Good morning. This is Geometry Lesson 5.3, Making Conclusions from Givens, or as we commonly call them, one-step proofs. One-step proofs. So you're going to be able to recognize and solve proofs by making conclusions from givens. So it's as simple as just completing one step. That's really what it amounts to. And this lesson is actually going to be supported by a one-step congruence worksheet. Which I'm going to be uploading separately. And you must, again, as you know, take notes on this lesson and make sure that you include your header. Here's all the information. Make sure your first and last name is printed legibly. There are no abbreviations or aliases. And that you can also show me in plain printed language the date, the period, and the lesson notes and name and number. Okay? And if you email it to me, make sure the same information is on your header. And you have until Saturday at 11:59 p.m. to send these to me. All right. Now, the basic premise here is that logic proofs can, not always, but they can be solved in one step. All right. And so why am I showing this to you at this point? It's because I want you to see, you know, in the simplest of terms, how you can come up with a logical proof just by making one statement, okay? And so there are two types of reasoning that underlie these proofs, and they're called inductive and deductive reasoning. And inductive reasoning is based on past observations. So it might be that you have observed that every 24 hours the sun comes up in the morning. And, you know, all your life you've observed that, and you've never come up with a situation where the sun didn't come up in the morning. So that reasoning is, again, based upon your observation. Deductive reasoning is based on past proof statements. So, for instance, let's just say that a comet passes the Earth every 96 years. Well, most people don't live for 96 years. So for most people, that's not something that they would have observed in the past and been able to make a note of it. But scientists would have, and in the older days, philosophers and magicians and such, would have noticed the passage of a comet, and they would have recorded it, and then they would have kept a record of that, and then their successors would note it again, and they would sooner or later discover that, hey, every 96 years it's going through our area. And so that is reasoning based upon past statements. So that's called deductive reasoning, okay? And either of these proofs are considered true until disproven. So that's a counterexample, okay? And we've talked about counterexamples previously. Now, you know, when I started out this unit on logical statements, we started out by talking about what logical statements were, if-then statements, hypotheses and conclusion, the fact that you've really been using them in different classes for quite a long time. And then we went on, and yesterday I introduced you to algebraic proofs using two-step proofs, which is something that we will be using today. And I'm sorry, not two-step proofs, two-column proofs. Two-column proofs. We're going to use a two-column proof today, but just in one step, whereas with the proofs that the algebraic proofs we did yesterday, those had more than two steps. Not a lot of steps, but you just need enough steps to prove your case. That's all it is. And sometimes it can be one step. So here's an example. This happens to be an algebra problem or math problem. For any number a, that's your given, you've got to prove that a equals a. So, with variables, that's particularly important. X has got to equal X. so that, when we substitute, we can come up with a correct answer. So here we've set this up as a two-column proof. The given is any number A. We have to prove that A equals A. And this is what you always see in a two-column proof. It starts out with a header just like this. Then you get your statements and your reasons. So the first statement is your given. So we write the statement and then we write the reason given. The second one is what, in this case, what you're proving, A equals A. Now, the reason why we can do this in one step is because it just so happens that the reflexive property proves that A equals itself. Where did I find that? Well, if you go back to the lesson that we did from yesterday, we covered that particular issue. And we've showed that the reflexive property indeed would cover this situation. So there you have it. It's proven. Okay, so now we're going to do several more examples. So now we're going to do a geometric one. So we're talking about point A and point B. So I'm just going to draw this up at the top. Here's point A. And they say between point A and B, well, what happens between point A and B? We don't know. Let's just, I don't know, let's put point B over here. Right here. Okay. Now, if I were to prove this, it says between 2 points, there only exists one line. I could do that by observation because I have 2 points, A and B, and notice between A and B, I could only come up with one line. Just one line. So I've proven that. And that basically is an example of inductive reasoning. It's through observation. So over here, the first thing I'm going to write is my given. So point A and point B. That's your given. And your reason, I'll put the reason over here first, is, well, this observation. Now, what do we call this observation? Whenever something is done by observation, it's so obvious that it's true, it's inductive reasoning. And that sort of thing is called a postulate, something that is just so profoundly true, there's no other way to get around it. It's called a postulate. So this would be the linear postulate or definition of a postulate. So definition of a line. Linear postulate. Or definition of line segment. You could use either term. And of course, what is the statement? Well, it's between 2 points, there exists only one line. So the only real time I'm taking is writing this out. And there I've written it out. I had to squeeze the 1 in there. I'm just going to put a little caret there so that you can remember that. And that's how we would do it. So this is a good example of inductive reasoning, a good example of a postulate, something that is true because it's just observable and there's just no other way you could get around it. It's got to have only one line. Can't come up with a counterexample for that. Okay. Here, the given is AM is congruent to MB. So here's A to M, and it's congruent to M to B. Now, we know this because it says that. All right? Also, you'll notice there are tick marks between A to M and between M to B. There's a tick mark in each spot. So that also is telling us. So a record here is telling us that AM is congruent to MB. So that's an example of deductive reasoning, right? And so prove M is the midpoint of segment MB. All right, well, so the given is AM is congruent to MB. So line segment AM is congruent. I'm using notation here. Is it congruent to line segment MB? And it says, and given, of course, is the reason. And therefore, M is the midpoint of MB. And what's the reason? Well, again, it's the definition of congruent segments. Now, you may not know this. You knew the algebra one that we did at the very beginning because I gave you a list of algebraic proofs. So that was easy. This one here, you were able to look at the observation and say, yeah, I think Mr. is right because, you know, it's obvious that this is the case. I can see it myself. But this one here, where somebody else had to tell you the information that told you this is congruent. If you didn't have these tick marks, if they didn't tell you that it's congruent, you wouldn't know that it's congruent. You just see A, you would see M here, and you would see B in the line segment, but you couldn't prove that M is the midpoint without the additional information. So deductive reasoning gives you that, all right? And then the actual statement for this, there's a list of these, and we're going to start to maintain that list now that we're getting into proofs, okay? One more to go. All right, so it says given line L is parallel to line M. All right, so they give you the information here. They don't put it in here, but I'm going to just add it because it tells me this here. I can put it here. So I put the little arrow symbols here to show the two lines are parallel, okay? And I would suggest you always do that whenever you're doing a test or whatever worksheet or whatever it is you're doing. You draw everything in completely, even though it's written over here. Get it all on one piece of paper because then you can see things. They want you to prove that angle 1, here's angle 1, is congruent to angle 8. Here's angle 8. All right. So you got two parallel lines and you've got a transversal. You have two different intersections. And you'll notice you've got all these numbered here. And 1, 2, 3, 4, 5, 6, 7, 8. So they're in two groups, two separate groups. So what these are is two separate intersections of parallel lines. And so that means then that we've got corresponding angles. And so again, that's something that you need to have known from somewhere. And in fact, we did this unit, covered this, and you know about corresponding angles. You should be able to remember that. But we'll create a list of this stuff that you've already done, give it to you so you've got more to go on. Corresponding angles is the reason. So let's go ahead and write this out. So the first thing would have been the given. So line L is parallel to line M. Okay, and the reason was given. And then the second statement was what was proved. Angle 1 is congruent to angle 8. Okay? And the reason is definition of corresponding angles. Okay? It's as simple as that. Now, corresponding angles are found when you have two parallel lines and have a transversal running through it. Then you would see the corresponding angles. Okay. All right. So that's basically it. We've covered everything for this, and I'm going to have the worksheet out to you later in the afternoon here, hopefully earlier than that, and we can continue on. Thank you very much. Bye-bye.